This is a financial maths question from the 2014 sample paper. So it's paper 1, question 8. Let's start. Padraig is 25 years old and is planning for his pension. So that's the first important number we have to take note of. He's 25 and he intends to retire in 40 years' time when he is 65. So we'll write down that and we'll make our own timeline on top here of what's happening. So when he's 65, he retires, and that's a 40-year gap. Now, there are two parts to this question, really, two main parts to it. First, he calculates how much he wants to have in his pension fund. So that'll be the first part of the question, finding out how much he needs to have in here on his date of retirement. And the second part is how does he get that money in there, basically, because it says then he calculates how much money he needs to invest in order to achieve this. And also throughout the question, we can assume that the interest rate is 3%. So the first thing to do, I suppose, is to convert that to a decimal. So it's I is equal to 0.03. Now, part A is write down the present value of a future payment of 20,000 in 1 year's time. So what we're doing here is a payment in 1 year's time. We're bringing that back to its value on the day of the pension, the day of retirement, and it's 20,000. So when you're bringing back money, when you're bringing money back in time, you divide. When you're bringing money forward, you multiply to work out the interest. So it's 1 plus I to the power of 1. And of course, I is 0.03. So the answer is 20,000 over 1.03 to the power of 1. And you get an answer of, on the calculator, 19417. 0.4, we'll say 0.48 rounded off. So that's the first part done. Now, part B. In part B, we really generalize what happened in part A. So it's for any number of years t. This was for 1 year. So we're going to generalize that for t years. So 20,000 for t years. If you bring it back t years, what's its value on, again, on the day of retirement? It's worth 20,000 over 1 plus I. And in this case, we might as well put in the I straight away, which is 1.03. And it's to the power of t this time. And if you and that's it, that's the answer to part B. He wants it in terms of t, so that's what we've done. Now, part C. Padraig wants to have a fund that could, from the date of his retirement, give him a payment of 20,000 at the start of each year for 25 years. So now this part of the question starts when he's 65. And what's happening here is there are payments. So he gets the first payment on that date of 20,000. So let's put that down here, the first payment. And he gets the second payment at the start of the next year, and so on. So we'll put that payment over here. We'll stagger these payments. And excuse me. So this happens for 25 years. But of course, let's bring all these back. We have to bring these back to their value on the date of retirement to get their true value on that date. So it's 20,000. And this is where the work we did up to now helps us. We've already got some of this worked out. So 1 year earlier, it's only worth 1.03 to the power of 1. And now his third payment of 20,000. So this is only worth, if you bring it back 2 years, 20,000 over 1.03 squared. And so on. So maybe do one last payment, 20,000, and bring it back. So this is the fourth payment. So that must be brought back 3 years. It might be no harm at this stage, before we go any further, to distinguish between payments and years, because they're one out from each other, basically. So let's say, in terms of payments first, that's the first payment. That's the second payment, 20,000. That's the third payment, 20,000. They're all 20,000 payments. So we'll say that's P for short payments. And we'll do another one above it, years. That's year 0. So that's 0 years from his retirement date. That, in other words, that is his retirement date. And that's 1 year later, that's 2 years later, that's 3 years later. So you see they're one out of step from each other. So it's worth keeping a track of that as well, because that's quite important later. So now, if we fast forward basically to the last payment, he said 25 years. So we'll say there's 25 payments. And going by the numbering scheme here, you can see, well, payment 4 corresponds to year 3, so 25 would correspond to year 24. So we put that in there. Now, that means we can get the last payment if you, again, look at the way the numbers correspond for us. So, for example, the year 1, it was to the power of 1. Year 2, you have to bring it back to the power of 2. Year 3 to the power of 3, etc. So that should be a 3 there. So we just put in the 3. And okay, so it's going by the year basically. So if you jump forward to year 24, it's going to be to the power of 24. So if you come back to this one over here, so it's 20,000. And if you bring the arrow back, that's to the power of 20,000 over 1.03 to the power of 24. So we'll skip all the ones in between. Obviously, we can't write them all down. We just want the pattern is what we want at this stage. So that's it. That's all of our payments of 25 payments of 20,000 brought back to their value on the day of the pension, the day of retirement. And that's what this is all about in this step. Now, what else does he want here? He wants us to show how to use the sum of a geometric series to calculate this value. So the idea is when you add all these together, all their values on the day of retirement, you get the value of his pension fund basically. So we're going to add all those together now to get the fund. And to do that, we write them out horizontally. It's easier to see. So the fund is equal to, so it's 20,000 was the first payment. And then if you look back there, it was 20,000 over 1.03. The next one was 20,000 over 1.03 squared, etc., all the way up to 20,000 over 1.03 to the power of 24. And we can, to calculate that fund, we can simplify life for ourselves. We can take out the 20,000. That's a common factor for all those terms. So it's into 1 plus, now if you take out the 20,000 from the fraction, there's a 1 left above the line. So it's 1 over 1.03 plus 1 over 1.03 squared, all the way up to 1 over 1.03 to the power of 24. And now we can recognize what's inside the bracket as a geometric series, which is what he's looking for. If you look at that carefully, you'll see that there's the first term, A is 1. The common ratio, R, is the fraction, 1 over 1.03, because if you multiply 1 by that, you get the second term. Multiply by itself again, you get the third term, and so on. And the number of terms in the sequence, N, is, let's count them carefully, because we've got to be careful here as well. So that's the first term, that's the second term, that's the third term. So the third term, you'll notice, is to the power of 2 down here. So vice versa, and the same with the second term is to the power of 1. So we'll put a 1 in there, for example. So it's always 1 out, basically. So that means that the last term must be the 25th term, because that's the power of 24. So just be careful with that in. It's 25 terms. And now we can use the formula. So the formula is Sn is equal to A into 1 minus r to the power of n over 1 minus r. And fill those numbers in. So it's 1 into 1 minus 1 over 1.03 to the power of n, which is 25, all over 1 minus 1 over 1.03. Okay, so now just let's work out that. And it turns out that there's a shortcut for working out that as well. And the shortcut on the calculator is get that fraction first. So I'll just show you here. So type in your fraction on its own first. So it's 1 divided by 1.03. Hit the equals button. Now that's saved under answer there beside equals, ANS. So the next time around, we don't have to put it in again. So now just put in 1 minus answer. So 1 minus answer to the power of 25. So it's the power of 25 divided by 1 minus answer. And you get 17.9355. Okay, and the last part in, not forgetting, we got to multiply by 20,000 to get our total fund. You see it there in the formula. So multiply that by 20,000 and we have an answer of, if you round that off, I suppose, to the nearest euro, it's 358,711. So it's equal to, so the fund is equal to 358,711 altogether. And that's that part done. Now at this stage, you might take a break from the question, see what we can learn from these figures and get a feel for these numbers, which is very important really for future reference. So I'm going to bring that up to my timeline on top, 358,711. So 358,711. So let's see the big picture here. That represents my pension fund on our Padraig's pension fund on the day he retires. It's worth 358,711. Now, from that pension fund, he draws money out for the next 25 years. He draws out actually up to he's 90 or so. He's going to draw out, let me see, he draws out 25 payments of 20,000. So let's work out that. If you get 25 payments of 20,000, so 20,000 multiplied by 25, you get 500,000. So you can see the power of compound interest here. By having 358,000 roughly in his account when he's 65, that gives him the power to draw out over 25 years 500,000 because of the interest added on during those 25 years. Okay, now on to the next part of the question. Now we have the second problem. We fixed the first problem, is how much does he need to have in his pension plan. We know what that figure is now when he retires. The next problem is how do we get that money in there? So he has to start planning it way ahead when he's working, during his working life. He has to plan ahead for this. So that's what's happening now. He's planning ahead. And we start when he's 25 years of age, and he's going to start investing money every month because that's when he gets paid. So now the other thing that's happening here is the units of time, I suppose, have gone from years to months. Everything's worked out in months now for this part of the question because he gets paid by the month, I presume. So let's work out that. So he's done the first part for us here. The 40 years he's working between 25 and 65, 40 by 12 gives us 480 months. That's the first part. That's the first part converted to months. Now the second part is to convert the interest rate to months. The interest rate of 3%, which is an annual interest rate. It's not just as simple as dividing by 12, because the way compound interest works, it goes up unevenly every month. It goes up more and more every month, so by unequal amounts. So we have to use a formula for that, and the formula is the monthly interest rate is 1 plus the annual or yearly interest rate to the power of 1/12 minus 1. Now, there's a formula like this in the table, but it's not quite the same. I think this one is easier to use, so it's well worth learning off this one. And if you fill in that formula, you get 1.03 to the power of 1/12 minus 1. So on the calculator, if you work that out, we get 1.03 to the power of 1/12. So just go back on that. So it's the power of 1/12. And we need our minus 1 at the end. And you get, as a decimal, 0.002466. So that's our monthly interest rate. Now, part 2, write down in terms of N and P the value on the retirement date of a payment of P. So now we're planning forward. We're putting in money P, and we're trying to work out what's it worth in basically N months, in N months time. So that's P into 1 plus, let me see, so it's the new interest rate now, of course, which is 0.00, everything is in months now, so it's 2466 to the power of N months, so it's N months time. And that's it, that's that part done. And again, that's getting us ready for the next part, because the next part is going to make 480 monthly payments for the 40 years of his working life. And we're going to work all those out one by one as well. So the first payment, when he's 25 years of age, so now we're starting the question when he's 25. And that first payment, if you bring it forward, the whole 480 months, it's going to gather interest of P into 1.002466 to the power of 480. Now, the second month that he's working, he's going to pay in an amount P again, whatever P is. If we bring that forward, that's worth P into 1.002466 to the power of 4. So it's 1 month less, so it's 479. And the third payment, etc. So the third payment will be gathering 1 month less interest again. So that'll be P into 1.002466 to the power of 478. And you keep going on like that until you get to the very last payment, which is the very last month before he retires. So that'll be gathering interest for just 1 month only. So P into 1.002466 to the power of 1. And again, the idea now is if you add all those payments together over his 40 years working or his 480 months working, if you add them all together, they add up to the pension fund. And the pension fund, as we saw earlier, was 358,711. So they all add up to 358,711. Now it's just a matter of doing that calculation. So write them out horizontally, I suppose. So if you line them up horizontally, you have P times 1.002466 to the power of 1 plus P into 1.002466 squared, etc., all the way up to the end. And the very last payment is we're going in reverse here, so it's the 480, it's the power of 480, so it's P into 1.002466 to the power of 480. So that's it, and that's of course equal to 358,711. So 358,711 is all of those added together. Okay, so we'll just right now that's equal to, if we just work these out now, again, if you look at all those in a line, we can take out the common factor, which is P. P is common to all those terms, so take P outside the bracket, and you're left with P into 1. P is into 1.002466 plus 1.002466 squared, etc. Again, all the way up to 1.002466 to to the power of 480. And yet again, we have a geometric series. So A, the first term is 1.002466. The common ratio is also the same number, 1.002466. Because if you multiply the first number by R, you get the second number and so on. And the number of terms, again, let's just number these to be sure. There's one term there, there's the second term. So there's the 480th term because the powers match. So n is 480. Now we need to make some space here, so I might just make a box up here to finish off the question. And so what we've got is a formula now again for geometric series. So it's Sn is equal to A into 1 minus R. So this is in the tables again, over 1 minus R. 1 minus R to the power of n over 1 minus R. And you fill in those. A is 1.0, so we'll just take down that. So it's 1.002466 multiplied by 1 minus 1.002466 to the power of 480 over 1 minus 1.002466. And again, we can use that shortcut on the calculator for working out that. We can just type in that number once, that R or A. So 1.002466, hit the equals button. Now that's saved as answer. So for the next part, all you have to do is hit answer multiplied by 1 minus answer to the power of 480. And bring down the bracket. And under the line, it's 1 minus answer as well. And you get 919.38. Now, that's not the end of it, because don't forget, it's that multiplied by P. If you look down here at the rest of the question, if you look down here, it's actually that geometric series multiplied by P here gives you 358,711. So what you have to do actually is the answer we just got. So you take 358,711 and you divide it by that number. So if we get the calculator back out and find what that number was, and so 358,711, and if you divide it by 919.38, 10223. So we'll try that on a calculator here. Actually, it's probably easier. So 358,711 divided by 919.38, 10223, and we get 390.17 rounded off. So it's 390.17 rounded off. So that's the, no, that's not SN, that's the payments. That's the individual payments that he pays each month out of his salary into his pension fund. 390.17. So now let's take that back to our chart here, 390.17, and write it here. So 390.17. So what we're saying is, again, we're finished that part of the question now, but I'm just trying to get something extra out of it so we can learn some more about financial maths and get a feel for these numbers, as I said earlier. So multiply that by 480, because there's 480 of those payments. So again, 390 multiply 0.17 multiplied by 480 gives us a number 187,282. 187,282. So 187,282. Now, what does that mean? So now we got a very interesting overall picture of what's happening with this pension fund. So this guy pays in over the 40 years that he's working in monthly payments. They all amount to 187,000 roughly. And by doing that, because of the power of interest, he ends up with this in his account on the day he retires, which is almost twice that. So it's a good investment, obviously. And not only that, but what he ends up with on the day of his retirement even grows further while he's drawing it out over the next 25 years. It grows to a total value of 500,000 because of interest again. So there again is the power of compound interest and the value of having a pension fund and the value of paying into a pension fund starting as early as possible in your working life. And that's about it from this question. There is one more part, but the last part is very easy. It's just working out for 10 years less. So you just readjust your formula, the same formula. It's the geometric series again. Uh, but there's the important lesson from this. As I said, the value of the compound interest and the way your pension grows over time because of that interest. And that's the end of this financial maths question.